your title? Scattering amplitudes?
Yeah, that's... I love this big chalk.
Yeah,
Do you have more of it?
So those boxes are full of the big chalk.
Ah, okay, excellent. Thanks.
I gather some of the other speakers prefer this thinner.
Well, let me try it.
Yeah, this seemed to be popular.
Okay, that's also good, yeah.
Ready to go?
I am.
All right, so let's get started. So welcome to week 4. Really the last week. So if I see you all sitting here next Monday morning, then I know you got locked into the eternal loop and it's time to go home. Like one more week of exciting and thrilling lectures, and we're happy to kick it off with Mark Spradlin, another member of the TASI class of 1999, who's going to tell us about scattering amplitudes. So welcome, Mark.
Thank you, and I must apologize due to a misunderstanding on my part. I got an email from Tom DeGrand saying that nobody comes to the 9 a.m. lectures in the 4th week, so that's why I volunteered to do the 9 a.m. lectures in the 4th week. Then I realized I misread the email, and it actually only says that not everyone comes to the 9 a.m. lectures. So what would have been my incentive to volunteer for this time? I don't know. Okay, so I've been given the task of lecturing on scattering amplitudes, which is an enormously huge field. 5 years ago, there was an entire TASI dedicated more or less solely to this topic. And like all the subjects that you're learning here in TASI, there's a huge gap between, in most cases, there's a huge gap between where your courses end, where your graduate coursework ends, and where the forefront of research begins. Now, there's no way I can possibly bridge that gap in only 4 lectures, so I have to apologize in advance that I have to be extremely selective about the topics I'll choose to cover, and they will be largely chosen, according to my own bias, a couple of hot topics here and there. But let's start just at the very beginning with some basic warm-up exercises that give you a gentle introduction to this field of scattering amplitudes. So we begin with the definition of a particle following Wigner. Who suggested to think about a particle as an irreducible representation, a finite dimensional irreducible representation of the Poincaré group. And in generic quantum field theories, when you're interested in quantities like scattering amplitudes, this is a reasonable approach to take because it's a nice discrete way of thinking about what a problem is. In ordinary quantum field, in a typical quantum field theory, especially when I say that I mean a non-conformal field theory, there are in general an infinite number of different field operators that any of which can be used to create the same asymptotic state. That's very different from the situation in a conformal field theory where there's a one-to-one mapping between local operators and states. So because of this enormous redundancy in how field operators are mapped to asymptotic states, it's good to just put aside that whole infinite redundancy and focus on the discrete problem of understanding the states themselves. So the first step in reviewing Wigner's classification is to recall that any 4 momentum p mu falls into one of 6 orbits under the proper orthochronous Lorentz group. SO plus 1, 3. We can either have p mu being identically 0 in which case the only relevant irreducible representation that's finite dimensional is the trivial representation. Or we can have p squared greater than 0. And for this I have to specify that I'm working in signature -1, 1, 1. So if p squared is greater than 0, this describes a tachyon. So let's not consider this possibility. Then the other possibilities are we could have p naught less than 0 and p squared equals to 0. P naught greater than 0, p squared equals to 0. A 4 vector satisfying this criteria cannot be related to a 4 vector satisfying this criteria if you restrict yourself to the proper orthochronous Lorentz group. Or you can have p naught less than 0, p squared less than 0, or p naught greater than 0, p squared less than 0. So these are the 6 orbits. Every 4 momentum falls into exactly one of these 6 orbits. And within each of these 6 sets, every possible p vector can be related to any other p vector by a proper orthochronous Lorentz transformation. So these two have negative energy. So we disregard them as physical states. Now, of course, when we talk about scattering amplitudes, it's often useful as a notational trick to allow ourselves to use both positive and negative energy states in order to keep track of who's an incoming particle and who's an outgoing particle. But for the purpose of classifying valid physical states themselves, we'll ignore them. So the only two of interest are a positive energy massless particle or a positive energy massive particle. Okay, now let me discuss briefly the construction of one particle states. For that, first I should mention, this is the important point, that in these two cases, it's always possible to find a Lorentz transformation that puts any such vector into canonical form. So I'll write here the canonical form. If you have a massless particle, you can always, by a suitable rotation, go to a frame where it's traveling at the speed of light along the z-axis. And if you have a massive particle, you can go to the rest frame. Okay. So in order to construct the one particle states, oh, and by the way, I am intentionally lecturing at what I consider to be a slightly elevated speed because I have a lot of material I want to get through, but please interrupt me if there are any questions, no matter how trivial you worry they might be. Okay, so we're going to construct one particle states. So the first step is to assume we have a basis of states that are labeled by the 4 momentum and whatever other labels are necessary in order to provide a complete basis. So the idea is for a given k mu, this set is intended to be a complete set of states of all possible particles that have that 4 momentum k mu. And initially, we're only going to define this. That's why I intentionally put k here instead of p. We're only going to define this for our reference momenta here. Then, and we assume that we have some unitary representation of SO plus 1, 3 acting on our Hilbert space. This representation is, of course, not going to be finite dimensional because this is a non-compact group. But it should be unitary because if we want to talk about quantum mechanics and we want to have conservation of probability, we should have unitary representations. Okay, so then we define P mu of sigma for general P by choosing some Lorentz transformation such that P mu is L mu of P comma K, K nu. Now this choice is not unique. That's an important point. I mean, that's the crucial point that will play a crucial role in just a few moments. But for the moment, just pick some. So you're interested in some form momentum P mu, and let's say it describes a massive particle. You choose some Lorentz transformation that takes the 4 vector that you're interested in and transforms it into the rest frame. And then you define...
Mark, you're missing the word.
Thank you. Thank you. Then you define P mu sigma to be whatever your unitary representation is acting on that state. Okay. Now let's ask the question, how do these states transform under a general Lorentz transformation? Okay, and here I'm going to need some more room, so I'll start at the top of this board. Let's consider some unitary transformation for some general Lorentz transformation acting on this state. We plug in the definition. Then we cleverly multiply by 1 on the left. Oops, sorry, there's a typo. So I'm using the well, let me finish writing and then, oops, another typo. Okay, so here I secretly inserted 1. That's what allowed me to put that in front of the formula. And then I use the fact that I have a representation of the group here. So when I have 2 u's multiplied together, or in this case, I'm going to have 3 u's multiplied together, I can pull all their arguments inside. Okay, so that UA, let's say U lambda 1, U lambda 2 is equal to U lambda 1, lambda 2. That's what it means for U to be a representation of the Lorentz group. Okay. Now, let's write this. Just want to collect the terms a little bit differently. Where W is equal to this monstrosity here. Now, here's the important point. And I apologize, I've dropped Lorentz indices everywhere in order to save time. So every time you see an L or an omega, it's a Lorentz transformation. Here's the important point. And you can see that this is true just by looking at the formula. Okay? Let's just read it. So imagine so W is a Lorentz transformation that's a composition or a product of 3 Lorentz transformations. First of all, it's a Lorentz transformation that takes K to P. So let's take a step back and imagine acting on K with this Lorentz transformation. First, this piece hits and it transforms K into P. Then we transform by lambda, which takes P into lambda times P. Then we apply this operator, this transformation, which is the inverse of the one that takes lambda P to K. So altogether, the net result is we start with K, we change to P, we change to lambda times P, and we change back to K. So the point is W is a very special kind of Lorentz transformation. W is an element of the little group, or a mathematician would say the stabilizer group, the little group of K, or the stabilizer group of K. That means the set of all Lorentz transformations that leave K untouched. Are there any questions at this point? Okay. So to finish our calculation, okay, so now by hypothesis, this was a complete basis for all states that have momentum K. Now if we go back here, this state has 4 momentum K. Because we just argued that this is a Lorentz transformation that doesn't change K. So this state has momentum, 4 momentum K. So by the fact that this is a basis, it must be that state must be expressible in that basis. So to continue the calculation, where am I? I have U of lambda, P of sigma is, I still have this thing sitting out front. Oops. Yeah, that's right. And then I have some coefficients. This formula is just expressing the fact that since that state at the other end of that board has 4 momentum K, it must be expressible as a linear combination of the states in my basis.
Really summing over sigma.
Sorry, thank you. You are going to keep me on my toes, and I appreciate it. Yes, of course. So to finish the calculation then, this operator passes right through these numerical coefficients and Lorentz transforms that K into lambda P. So this is the final result. We define these one-particle states for general 4 momentum, and if you do a Lorentz transformation on them, the result is, again, a linear combination of the expected states, the states that have 4 momentum lambda p, but there could be some non-trivial linear combination going on here. So the words we use are that these states live in representations of the little group. So the states P mu sigma live in representations, not necessarily irreducible, in representations of the little group. Okay. Now for massless particles, the little group is equal to U1 times E2, where U1 is rotations around K. Again, if we're using the reference where K is a null vector pointing along the z-axis, then this U1 would correspond to rotations around the z-axis. Cross with the Euclidean group in 2 dimensions, because, again, referring to that example, you can do arbitrary rotations or translations in the xy directions. Now, often we ignore this part for 2 reasons. Well, first there's the observational reason that massless particles in our universe are observed to always only live in the trivial representation of this. But also, perhaps more importantly, as I think I said long ago, though I don't remember if I explicitly put it on the board, we want our particles to live in finite dimensional irreducible representations. Now this group being non-compact, because it includes arbitrary translations in xy, the only finite dimensional irreducible representation it has is the trivial representation. So we can just ignore this piece. So that's why you'll often see people say that the Lorentz group, the little group for a massless vector is just the set of rotations at orthogonal to that vector. For a massive particle, the little group is SO3, or because we're working in quantum mechanics and we have to allow the possibility of allowing ourselves to use projective representations, or SU2, for half integer spin particles. I'll just say for fermions. These are the SO3 rotations. If you imagine putting the massive particle in its rest frame, then you can do an arbitrary SO3 rotation and it will stay there. It will still be in its rest frame. Nothing will have changed. Okay, are there any questions at this point? One more comment is that the eigenvalue, the U1 eigenvalue of a particle state, of a massless particle's massless state, is called its helicity. And it should be quantized by, again, essentially by a topological argument. It should be quantized in half integers. Okay. So I'm going to continue now. And again, because I have to do triage on what I can cover and what I can't cover, I'm going to consider the rest of my lecture only on massless particles. And this is a shame because sometimes it gives people the false impression that there's some fundamental reason why massless particles are better, or I don't know, something. The formulas that I'm going to introduce in just a second works equally well for massless and massive particles. It's just that it requires a little bit more notation and bookkeeping in the massive case, because SO3 representations or SU2 representations are ever so slightly less trivial than representations of U1. So we will continue by looking only at massless particles. If in a few months you see a paper on arXiv titled YATLA, then maybe it'll have a discussion of massive particles. YATLA stands for Yet Another Tazi Lectures on Scattering Amplitudes. Okay. In order to deal efficiently deal with the fact that one particle states should transform under this as U1 group, we introduce what are called spinor helicity variables. If you have a massless 4 vector, you can write it as a 2 by 2 matrix. And the condition that p squared equals 0 becomes the condition that determinant of this 2 by 2 matrix is 0. Now, if a 2 by 2 determinant has, if a 2 by 2 matrix has determinant 0, that means it's always possible to decompose it into two component objects. Basically, you're saying that if it has determinant 0, that implies that it has rank at most 1. So you must be able to express it in this form. This is in fact very convenient because you probably know that the complexified Lie algebra of the SO1, 3 Lorentz group is isomorphic to 2 copies of the SL2 Lie algebra. And those sometimes called SU2 or SL2 left and SU2 right. And those act separately on these 2 kinds of indices. So I'll just put this as a reminder. SU2 left and SU2 right act on alpha and alpha dot indices respectively. Okay, now if I give you, some p, it's clear from this formula that there is no unique choice of lambdas associated to that p. Just quickly to clarify, Oliver, I should end at 10:15. Is that
That's correct.
the understanding? Excellent. For a given p mu, there is no unique choice of lambda and lambda tilde because you can always rescale. For any non-zero w, now the important point that I'm going to explain is that this rescaling is exactly a remnant. I mean, it exactly reflects this U1 little group that exists for massless particle states. So in order to explain that claim, I'll put it in the form of a small exercise. Let k mu be k0, 0, 0, k0, and let L be a Lorentz transformation that rotates by an angle theta around the z-axis. You can check that, always worried about getting the signs wrong here. Under this Lorentz transformation, these two spinor helicity variables transform by picking up phases. E to the I theta over 2 and e to the minus I theta over 2. Okay, that's fine, because if these pick up opposite phases, then of course the form momentum is unchanged, and that's exactly what we expect. That's a defining property of the little group. So this is, of course, indeed a little group transformation. But it's simultaneously a useful bookkeeping device. So let me just make an aside. This is a relevant point to make this aside. In Minkowski's signature, lambda should equal plus or minus lambda tilde complex conjugate, so that p mu is real. And the sign here depends on your choice of metric signature and on whether okay, that's right. P naught is greater than 0 or less than 0. As I said before, physical states only have positive energy, but when we talk about scattering amplitudes, we want to have a formalism that will allow us to describe positive and negative, and formally describe positive and negative energy for momenta, so that we can have scattering processes with incoming and outgoing particles. But in general, it is useful to allow lambda, lambda, and lambda tilde to be independent complex variables. I mean, that's of course been a long-standing tool, not only in quantum field theory, but quantum mechanics way back to the beginning. Consider scattering processes as a function of complex momenta, and then you have at your disposal all the powerful mathematical tools of complex analysis to study this, for example, the singularity structure of scattering amplitudes in the complex plane, etc. So when we do that, when we allow lambda and lambda tilde to be independent complex variables, then this number, this W needn't be a phase. Okay, it can be in fact an arbitrary complex number. Okay, so now finally here's the point. We'll label massless particle states not by p mu sigma, but by lambda comma lambda tilde. Okay, with the property or more generally, let me write the formula and then I'll take a step back. And let me make one correction to the sentence. We'll label a massless particle state of helicity H. So the point is, we're going to use a notation rather than using this kind of notation where, unless you think about it for a second, okay, what are the two possible sigma values? Well, yeah, okay, I don't want to go on it's basically positive helicity or negative helicity, depending on, it could be. It's a complete set of states. Remember that this was meant to be label a complete basis for all states of a given form momentum p mu, and we've seen that these are characterized by a helicity eigenvalue. Instead, we're going to use a notation where we don't have to keep track of this auxiliary label sigma, and instead we're going to have the entire multiplet notationally built in this way. We're going to label our one particle states by lambda, lambda tilde, with the understanding that this scaling property here, which is what's required for it to transform correctly under little group, so I'll add a phrase here, which is required so it transforms correctly under the little group, is built in. It's built in to our notation. Now, why is that useful? Okay, and now for the first time, let me talk about amplitudes. A fundamental assumption is that the S matrix transforms, I want to say it differently. I want to say the Poincaré group acts on the S matrix. The Poincaré group acts on the S matrix describing, let's say, n particles, as it does on n individual one particle states. And I'll tell you exactly what that means by writing a formula. Suppose we have a scattering amplitude that describes some n particle process for massless particles. Describes a scattering of n massless particles so each particle here, each particle should be, in order to specify who it is you're scattering, you need to tell me for every single one of your n particles what their lambda value is, what their lambda tilde value is, and what the helicity is. Because this is the information that specifies a one particle state. So these are the n particles you're scattering, and I imagine that that's some scattering amplitude. And then the statement that I just wrote here in words, when translated into a formula, what that means is sorry, this is important, so let me make sure it's totally legible. Here I'm doing a little group transformation on particle I. So this is my scattering amplitude where I've done a little group rescaling of the spinor helicity variables corresponding to particle I, and I've left the others untouched. This should equal the overall factor of Wi to the power 2 Hi times the original amplitude, unscaled. This is the statement of what it means for the scattering amplitude to be Poincaré invariant for massless particles. And there's an analog for massive particles. Any questions at this point? Yes?
You said you could use this formalism also for massive particles?
Yes.
How do you modify this? I mean, you use the fact that the determinant was 0, right?
Yes. So you have to introduce a pair. Oh, thank you. Oh, the question was, earlier I said that you can use this same formalism. I hope I said very similar. I probably did say same. You can use a very similar formalism for massive particles. And the question was, how is that possible, since built into this formalism is the fact that the lambda and lambda tilde make the determinant of p being 0. And the answer to that question is, when you have a massive particle, we need to introduce for every particle a pair, 2 lambdas and 2 lambda tildes. So the lambdas and lambda tildes get an extra index. But that index also ties in very nicely with SU2 group theory indices. So it all works out beautifully, but it's a little bit more notationally cumbersome. Okay, let's introduce some notation. Now the point is, these brackets are by construction completely Lorentz invariant, because the Lorentz indices are all appropriately tied together. Both are Lorentz invariant. They are not, however, little group invariant, because obviously if we scale, let's say, the lambda for particle j by a factor of 1 over w, this thing will scale by a factor of 1 over w. So these are Lorentz invariant and have the obvious little group scaling properties. So let's discuss three-particle scattering amplitudes. Three-particle and I should say massless. By momentum conservation, these sum to 0. Again, we can, by crossing symmetry, we can choose to have, well, we always imagine, let's say, for example, one of the particles could be incoming and one could be outgoing, or vice versa. And so they satisfy this constraint by total momentum conservation. This implies that P1 plus P2 squared, oh yeah, that chalk is worse. Okay. Now I forgot to mention in this notation, you can check that Pi plus Pj squared is Ij times Ij, possibly up to a convention-dependent or signature-dependent minus sign. There we go. So this implies that 1, 2 equals 2, 3, 2, 3 equals 3, 1, 3, 1 is equal to 0. This is a very unusual feature of three-particle kinematics, the fact that all of these products must be 0. Okay, so you need to pick at least one of the, so there are different branches of solutions. You need to pick at least one of these to be 0, and at least one of these to be 0, and of course also at least one of these to be 0. But the minimum number you need to pick for them all to be 0 is 2. And the reason is that, notice that, for example, 1, 2 is equal to 0 if and only if lambda 1 alpha, lambda 2 alpha are parallel or proportional. It's just the same thing. These are two component objects. Okay? This is a determinant of two component column vectors, and that's 0 if and only if the two columns are proportional to each other. So similarly, 2, 3 is 0 if and only if lambda 2, lambda 3 are proportional. But if lambda 1 and lambda 2 are proportional, and lambda 2 and lambda 3 are proportional, then lambda 1 is also proportional to lambda 3. So if 1, 2 equals 0, and 2, 3 equals 0, then 3, 1 equals 0 also. So really there are only two distinct branches of solutions, although they intersect at a trivial common point. So I'll just write it like this. There are two distinct types of massless three-particle amplitudes. You can have either some arbitrary function of these three brackets and then the same thing with the square brackets, replacing them. Now, if your theory has parity symmetry, then the two are simply related to each other. But I emphasize that parity invariance is not necessary at all for any of this formalism. Okay. So, by virtue of the fact that I'm specifying that my amplitude is a function, let's focus just, for example, on the first case. Second case is entirely analogous. Just by virtue of the fact that I'm specifying my scattering amplitude as a function of brackets, it's automatically Lorentz invariant. Because the Lorentz invariant, so the brackets are Lorentz invariant, so any function of the brackets is Lorentz invariant. However, it does not automatically have the correct little group scaling. There is a unique function that works. And it is a is equal to 1, 2 to the power h3 minus h1 minus h2, 2, 3 to the power h1 minus h2 minus h3 times 3, 1 to the power h2 minus h3 minus h1. Up to an overall undetermined numerical coefficient. The argument that leads to this formula is exactly analogous to the argument. It's basically the same argument that you see in conformal field theories when you use the scaling symmetry to argue that the three-point function has a universal functional form on the 3 points. It's literally the same argument because here the little group exactly corresponds to rescaling these spinor helicity variables. And so in a conformal field theory you get like x1 minus x2 to some power of a linear combination of deltas, the scaling dimensions that look entirely analogous to this. Okay. One comment is that, well, okay, there are going to be many comments, but in order to have a smooth limit, in the case of Minkowski signature, oops. So remember that in Minkowski signature, let me take a step back here. If you were in Minkowski signature, if you required that this is the complex conjugate of that, then there's no non-trivial solution at all. All of these things have to be 0. The only reason you can possibly get away with having non-trivial solutions let's say, having a solution where this is 0, this is 0, this is 0, but this is not 0, this is not 0, and this is not 0, that's only possible if you allow yourself to relax the constraint of working in Minkowski signature. But if we want our amplitudes, if we write down formulas for amplitudes and we want them to have sensible interpretation at the end of the day, if we actually evaluate them in Minkowski signature, it had better be the case that we get a sensible limit. So looking at this formula, if you want to avoid having it blow up as you take the limit where all three brackets go to 0, we require that h1 plus h2 plus h3 be less than or equal to 0. So the way to see that, let me just do that quickly. You just put all these things to epsilon. So you get epsilon to the power h3 minus h1 minus h2 plus h1 minus h2 minus h3 plus h2 minus h3 minus h1, which is epsilon to the power minus 2 h1 plus h2 plus h3. So if you want to avoid this thing blowing up, you should impose this condition. So let me write it up here. And otherwise, A equals 0. Yeah.
So that formula looks like conformal symmetry. Not
Exactly.
Scaling symmetry.
Yeah.
So where can I see the conformal symmetry?
Well, yeah. Yes, thank you. The question was the formula and even the comments I alluded to earlier. The question was the only piece of the argument I used was scaling symmetry, but we know that the three-point function, the analogous formula in conformal field theory, also satisfies special conformal symmetry. So where do you see the special conformal symmetry in this formalism? And yeah, so that's a remarkable feature that this formula also has a special conformal symmetry, which, yeah, I wasn't prepared to say much about it today, and it would detour, but I think I will say more about it next lecture, because it's important. But also it's a little bit different because these well, okay. I'll see if I can say something more intelligent about that if I choose to. Yeah. Okay. All right. Good. I'm actually doing extremely well on time. So, good. Okay, but now it starts getting harder. So, all right.
No TASI lecturer has ever said that.
Really? Okay. Well, good. Okay. Let's consider maybe that's because no TASI lecturer has ever done so little in the first 50 minutes. Let's consider, for example, spin 1 particles. So when I say spin 1, I means I'm allowing states of helicity +1 or -1. Then this formula, so you just plug in h1 equals h2 equals h3 equals plus or minus 1 in various combinations. Here are the 4 combinations. And it's conventional to label our 3 part rather than writing lambda and lambda tilde every time and wasting lots of time and using up lots of blackboard space. I'll just write the particle index, like particle number 1. So this means particle number 1 has a negative helicity, particle number 2 has a negative helicity, and particle number 3 has a negative helicity. If we plug this into our formula, we get some undetermined coefficient alpha, and the rest is completely fixed. Okay? Or we could have, we could switch particle 3 to being positive helicity, and then we just plug it into our formula. Or we could go one more, switch particle 2 to plus. I'm running out of room, so let me lower it a little. One minus 2 plus 3 plus gamma times 2, 3 cubed and the last one has to fit on the next board. Are undetermined parameters. Oh, and I realized, yeah. Okay, let me call these 1, 2, 3, and 4. Because I forgot an important point, and good. Having more time in the lecture will give me back. You see here, numbers 1 and 2 only exist on the branch where 1, 2 equals 2, 3 equals 3, 1 equals 0, and 3 and 4, yes, only exist on the other branch. Okay, so you have to split there two. As I described over there on that board, there are two discretely different cases to consider. Those two discretely different cases intersect at a single point. They intersect when you restrict to Minkowski signature, and in that case, the brackets become the complex conjugates. The angle brackets become the complex conjugates of the square brackets. So except for that point of intersection, they're two discrete branches, and so when I've written these 4 different formulas here, I only got 2 of them from this, and I got 2 of them from the alternate formula that looks exactly analogous, except the angle brackets are replaced with square brackets. Yeah, that's right. So maybe I should write that. Yeah, you just flip the signs of the h's, you change the angle brackets to a square bracket, you flip the sign of the h's, and this becomes a greater than or equal to 0. So let me write that, just to get it on the record. You flip the sign of the h's because remember that lambda and lambda tilde scale oppositely. oops, that's H1 plus H3 minus H2 if the sum of H's is greater than or equal to 0. Okay, now here's one important point to understand or to appreciate is that these formulas are true beyond perturbation theory. They're completely exact. There's no room for any type of functional dependence other than what's shown here. The only thing that's undetermined is these overall coefficients here. So let me ask a trick question. You're thinking, wait a minute, I remember studying Yang-Mills theory in my quantum field theory 2 class, and I know he's going to tell me that these parameters here must be related to coupling constants, right? Obviously, the coupling constant should appear in front of a 3-particle amplitude. But the coupling constant, let's say if you're talking about pure Yang-Mills theory, it's not really a constant. It has a dynamical scale. It's a function of the scale that you evaluate it at. So my question to the audience, and it's totally a trick question, and senior people are not allowed to comment, if we were doing this analysis in pure Yang-Mills theory, okay, where we have a collection of gluons, which are spin 1 particles, how would I know what values these parameters take? Alpha, beta, gamma, and delta. What would determine the numerical value of those parameters, given that in Yang-Mills theory, they're not really constants, they depend on the renormalization scale, etc. Okay, and the trick question is, this is all completely irrelevant to that question because QCD does not have massless spin 1 particles, right? There's a mass gap, so due to confinement, there just are no massless states. So these formulas are applicable if your S matrix actually has massless particles in them. Okay. Now, one interesting comment is immediately obvious. Take a look at these formulas. All 4 of these are anti-symmetric under the exchange of any 2 particles. Like let's say you take this one and you exchange particles 1 and 2. This will get a minus sign. No, I'm sorry. 1, 2, 3, 4, 5, 1, 2, 3. Wait. Oh, don't tell me I'm going to screw this up. 2, 3, 3, 1. Yeah, I get 3 minus signs. Okay, that's a minus. I was really worried there for a second. You're going to get a minus sign here, and then this goes into that with a minus sign. That goes into that with a minus sign. So altogether, you get 3 minus signs. So here you have an amplitude for 3 spin 1 particles, which by the spin statistics theorem are bosons, and yet, that's really weird, there's a minus sign if you exchange any 2 particles. So that's an inconsistency. That tells you that all these coefficients must be 0. So in fact, if you only have a single particle, spin statistics tells you that alpha, beta, gamma, and delta are all 0. But you kind of already knew that because what is a massless spin 1 particle? It's like a photon, but a photon can't have any self-interactions. If you want to have self-interacting spin 1 massless particles, we know you need non-abelian gauge theory, which means you need more than one of them. So let's go back, and I'm going to go back to this formula. And imagine that I have several different species of massless spin 1 particles. So suppose there exist several species of particles labeled by A. Then I can have particle 1 being of type A, particle 2 being of type B, particle C being of type C. Now, the Lorentz and Poincaré group analysis is unchanged. So nothing changes at all with regards to these bracket formulas here. The only thing now is that these numerical constants can take different values depending on who are the particles that are being scattered. And now spin statistics tells us that alpha, beta, gamma, delta must be fully anti-symmetric. Under the exchange of any two indices. Okay, that's already a pretty cute fact. I mean, we knew that was true. But now let's finish in my last 5 minutes with the exciting fact where we will derive Yang-Mills theory. This, however, requires us to take a step. And here, at this stage, I need to rely on the crutch of perturbation theory. So this is a big difference compared to, for example, how the bootstrap works in conformal field theory. The problem is that these constraints coming from Poincaré invariance and unitarity that I will impose in just a second are simply not strong enough, or rather a better way to phrase it is we don't yet know how to utilize their full strength. So we rely on crutches, and the crutch that I'm going to rely on now is I will assume that 4 particle amplitudes are rational functions of the brackets because I know that when you work at tree level, let's say you have a Lagrangian and you work at tree level, every Feynman diagram you get is going to be a rational function, so when you add them up to get the amplitude, you're going to get a rational function. Now, if we had the power to compute fully non-perturbative S matrices without relying on the crutch of making assumptions about the analytic form that we get order by order in perturbation theory, they would look completely different than this in general, I presume. But at least on this class of functions, we know how to implement unitarity. In general, we don't know how to implement unitarity. But on rational functions which represent tree-level amplitudes, we know very well. It says that if you have some scattering amplitude, then it can have poles. It's a rational function, so the only singularities are poles. It can have poles when some intermediate particle goes on shell. So if this blob represents some generic scattering amplitude, it can have a pole at p squared equals 0 in a massless theory, where it factorizes into a product. In this case, since I'm considering a 4-point amplitude, it would factor into a product of 2 3-point amplitudes with a propagator 1 over p squared. All right. So with that assumption, let's write an ansatz So in general, Poincaré invariance allows, let's look at a 4-particle scattering amplitude, 1 minus, 2 minus, 3 plus, 4 plus. The little group analysis if you want to build something that has the correct little group scaling, you put a factor like this out front. And then you have here an arbitrary function of st and u, the Mandelstam variables. This function is undetermined. Just if just using Poincare and Poincare symmetry, there's no way to determine it. It's fully Lorentz invariant. But if you allow me to rely on the crutch of perturbation theory, then I can make a hypothesis. And this will be the very last step. We hypothesize that it should be a function with single poles simple poles, sorry, I meant to say simple poles, where the c's are coefficients. Now let's check factorization in the S channel. There could be additional terms that don't have poles. This argument would not see such terms. If we were working with a Lagrangian, these would be contact terms. Oops, and I'm out of time. So much for being early. This will be done in just a minute. If we look at the residue in the S channel, here's an S channel pole and there's an S channel pole. Now because S plus T plus U equals 0, when S is equal to 0, U is equal to minus T. So the last coefficient does contribute with a minus sign. Now if we use the factorization property to write what this is supposed to be equal to, it's supposed to be equal to a sum over exchange diagrams for any particle that can be exchanged between the left and the right blobs in that graph, where P is the momentum carried in that line. Now here I'm going to assign my second exercise. If you plug in the 3 particle amplitudes, which are completely determined, then you find that this is equal to sum over E alpha A, B, C, no, sorry, I wasn't using that, beta and gamma. Beta A, B, C, A, B, E, gamma E, C, D, E, times 1, 2 squared, 3, 4 squared over T. So we conclude that CST minus CUS is the sum on E, FABE, FCDE. Yes? Thank you. Yes, I do. Because if P is incoming to one of them, it's outgoing to the others. Okay. Now I'm really out of time, but I'm at the end of the argument. Because if you do the same analysis for the T channel and the S channel,
T and U.
Thank you, T and U channels, you find a solution exists only if the Jacobi identity is satisfied. And I skipped one step here. I should set alpha ABC equals beta ABC by parity. Then you literally get the Jacobi identity. So this is an amplitudologist way of understanding something that you've hopefully already seen from the point of view of Lagrangians, that the only possible way to have self-interacting massless spin 1 particles is if the coupling constants in the 3-point amplitude satisfy the Jacobi identity. But here we've seen it instead of from a Lagrangian point of view just by starting from the basic building blocks of scattering. So that concludes the first lecture. Thank you for your patience.
Questions for Mark?
Yes.
Yeah. What happens in the three-point amplitude when the sum of the helicity is 0?
Yeah, that's so the question was, what happens in the 3-point amplitude if the sum of helicities is 0? And that's a little bit of a delicate case. You can sit and classify the possibilities that are allowed. Most of them are not allowed. Obviously, one trivial case that is allowed is if you just have 3 scalars. Okay, if you have 3 scalar particles all having helicity 0, then the 3-point amplitude is an undetermined numerical constant. But you can have some other non-trivial things, like you could have a scalar coupling to 2 opposite helicity fermions, etc. So, but it's a little bit more subtle. So, yes.
How would you have to modify this argument that, not only self-interacting gauge bosons, but also fermions?
Could you repeat the question?
Yeah, the question was how would you have to modify this argument if you had not only self-interacting gauge fields but also fermions, and I assume you mean charged fermions that live in some representation of the Yang-Mills group, and then you could have a fermion exchange. Well, for lack of time, let me just say you should work out all the amplitudes for yourself as an exercise. I mean, you know that if you have Yang-Mills theory with charged fermions, all 4-point amplitudes satisfy factorization. So you should be able to work it out with the tools I've taught you.
All right, let's take a break and thank Mark
Okay.
again.
Very nice.
Thanks.
People have
You're not actually lecturing, you're just an organizer.
I'm
I
just lecturing.
You are lecturing.
Lecturing next.
Ah, okay. Okay.
I need to pre-write something on the board.
Yeah, well, I'll be a good citizen and erase.
But I think they usually come with
Is there more sophisticated erasing
more
procedures?
sophisticated
Well,
water-based.
Okay.
Sophisticated is the word I would use. It's effective.
Did you have a question?
Can I ask you a question real quick? Maybe this is a dumb question, but so yeah, I guess you enumerated like all these possibilities. I guess I just want to make sure I understand this. I
Yeah.
guess like the logic here, right, is that like the amplitude has to be written in terms of like square brackets instead of angular ones here because
Because in this branch the others are all 0. Yeah.
Thanks.
That's all.
Starting now, it should be all right.
We didn't love it. We felt it was a little pretentious.
Hi, how are you?
The lecture is really good.
Okay, thanks. Good.